Good afternoon, everyone. My name is Michael Dickens. I'm a research scientist with High Performance Research Computing at Texas A&M University. And today I'm going to show you how to access CryoSPARC on the ACES cluster. And also we'll have a detailed demonstration which you can follow along. If you have any questions at any time, you're welcome to unmute yourself or ask in the chat. We have a number of staff on hand that can help you with that. So the slides for today, from our main website, you can go to training courses. This is where you register. And then you'll see intro to CryoSPARC, view details, and then you can see the latest release, latest version here. Now in the future, this CryoSPARC is going to move to this previous courses tab. So if you don't see it in this tab, click previous courses. Okay. All right. So I'll cover how to get started. You'll need an academic license ID, which you can get free from CryoSPARC. We'll go over the computing resources, logging into the ACES portal and starting a CryoSPARC job. Then we'll talk about a little bit about CryoSPARC Live, and then we'll have most of this course will be the interactive tutorial. All right, so the CryoSPARC academic license ID, you can use that. You can apply for that. Use your university email, and you'll receive an ID from CryoSPARC within a day or two, and you'll need that to launch a session. And you can only use your license at one time. You can only launch CryoSPARC one time. You can't launch two instances of CryoSPARC on ACES. You can only launch one. You could reuse your license. I've had mine for a number of years. All right. So this is a picture of the ACES cluster. We have the Open On Demand portal installed. I'll back up about the license. The license is here on the slide. It's also on the course registration page. Right here. Go here. There's a link here. If you don't have the license, you can apply and get your license and follow along with this tutorial later. We are recording and we'll post it in a few weeks. And you want to use the latest recording, which we'll have available in a few weeks for this session, because we have a newer version of CryoSPARC installed, the latest version, as opposed to the last recording we have, which is an older version of CryoSPARC. Okay, so we have a number of H100 GPUs. We have, generally we have two. They range, the number of GPUs per node range from 2 to 8. We have some A30 GPUs, and there's a lot of other nodes. There's some CPU nodes, and then there's also some other nodes with other accelerators that CryoSPARC does not support the other accelerators like the PVC GPUs. Just a reminder, you want to specify enough time to allow your processing to complete. If you launched a job, let's just say you launched a job for 12 hours and you're into your 11th hour or your 10th hour, or even before the end of the workday, you can send a request to extend your job, your current job. Just make sure it's during business hours and central time. It probably will not get extended if it's on a Saturday or Sunday. And if you launch a job for 24 hours and you're done in less time than that, and delete the portal job, and that way you can free up the GPU resources for other users. And we'll show you how to do that. Okay, so as kind of mentioned earlier, you can only launch one CryoSPARC portal session at a time. But within the CryoSPARC session, you will able to launch multiple jobs. Um, you can if you need to import images, you can start a CryoSPARC session with CPUs only. The GPUs are in kind of in high demand. Sometimes it can take an hour or more for your session to start. But if you want to import images, you can just start with a CPU node. Okay, if you've launched a GPU job and it's still pending, but by the time you're leaving for the day, you want to go ahead and stop that job because if it starts in the middle of the night, then you'll be charged service units for the job as it starts, and you're not doing anything, and also it'll prevent resources from being idle. Um, PVCs are not supported. Um, and submitted jobs can have a delayed start time because of the high demand of some of the GPUs, or may have a maintenance, and I'll show you how to tell to see if we have a maintenance. Okay, so let's go ahead and log into the ACES portal. From our main web page, you can select Portal, ACES Portal Access. So we actually have to select some specific options for for this um, for this course. I'll show you what those are. So once you select once you select Portal ACES, you might reach or you will reach this ACES this access login screen. I've already logged in, so that's why we didn't see it. I didn't have it pop up. But if you do have this or when this pops up, select however you registered with Access, either use Exceed or your university account or your institution, and then use your Access ID and password, and then you have the two-factor authentication to log in. So let's go ahead and do that. And let's see, give a thumbs up if you have logged into the ACES portal. When you do log in, you'll see the portal like this. So let's give everyone a few minutes, and if you have any questions or need some help, feel free to unmute yourself and ask, or ask in the chat. So give us a thumbs up if you've logged into the portal. Okay, um, I just found my tab with all the users. So give me another thumbs up if you logged into the portal. Okay, I see 1, 2, 3. Okay, so I'll just assume everyone else wants to follow along. Again, we are recording this. So now let's get back to the slides. All right, so now we're going to select My Interactive Sessions, and we're going to select this CryoSPARC short course. The CryoSPARC short course is only going to be available for today. If you're watching this on YouTube, you'll select the newest CryoSPARC. 421 is the older CryoSPARC. It may not work for new users, so if you're new and you're not in the short course, use this CryoSPARC 471. But for today, we're going to use CryoSPARC short course. We've got 471, that's the latest version, and you want to input your license ID here. You want to select the H100, and then number of GPUs, we're just going to leave it at 1. Make sure you leave this at 1. Just leave that at 1. Number of hours, we can make this 4 hours. Number of cores, you can select 12. Gigabytes of memory. CryoSPARC recommends 32 gigs if you're using 1 GPU and 64 if you're using 2 GPUs. We're just using 1, so we're gonna select 32. But since we have more available, I'm just gonna select 48. Because what we have is we're sharing a node that has 8 GPUs, so we have to limit the memory to 660. Now you need to select advanced options and need to select CryoSPARC. We have a reservation for these GPUs so that we can run our jobs. So if you launched CryoSPARC earlier and you didn't select this CryoSPARC reservation, your job's probably queued, and because the GPUs are busy. One other thing I wanted to show you, you can select GPU avail and see the availability of GPUs. You can see right now H100s are busy with other jobs. We have a lot of PVCs, but CryoSPARC doesn't support PVCs and it doesn't support this vector engine. So here's the configuration. We have 3 nodes that have 4 H100s attached. We have 2 that have 8 and 1 that has 2. We also have 1 node that has 2 830s. So for today, we're going to select CryoSPARC reservation, 1 GPU. Make sure you select H100. You input your license ID and then click launch. All right, so this takes about 4 or 5 minutes, maybe 5 minutes to start. So we're going to go on and look at some other things. Okay. Okay, there's a GPU debug. There's a H100 and GPU debug. So that GPU debug is, if I'm to go back here, if I'm to look right here, GPU debug, it has a max of 2 hours. So if you can get something done in 2 hours, you can use this GPU debug. But this one can't be extended because this is for short processing. But if you can use it, this one's usually more readily available than a full GPU for the maximum time. Okay, so it says my session is currently starting. When it does start, this is your login and password. Okay, we did that. Okay, now for ACES shell access, sometimes you'll want to create the directories. You can do this a couple different ways. I'll show you. You can use files and you can go to Scratch here. And then you can come in here, you can create a directory, make a new directory in your Scratch directory. But what I want to show you is clusters ACES shell access. And here you can see your quotas, message of the day, but you can also see if we have, just type in maintenance and it'll let you know if there's a maintenance scheduled. This is a way to make, from this command line, to make a directory. You want to go to your Scratch directory first and then make directory. If you want to create multiple a directory tree like this, but the CryoSPARC projects directory doesn't exist yet, you can use the -p flag and you can create multiple new directories. So I'm just doing this because later I want to show you when you're adding data to CryoSPARC Live, you'll want to have a data directory. Of course, you can name this whatever you want, but make sure you use your Scratch directory. There's also a project directory, which your Scratch directory has a beginning quota of 1 TB. You can see mine's at 1 TB, but we also have or this one, this is my Scratch directory. I've got a max of 1 TB, but we also get a project directory which has a max of 5 TB. So if you want to work in your project directory, just run the show quota, and it will show you your project directory. And you should see the max is 5. Your project directory should say 5 TB. If it doesn't, let us know, and we'll fix that, because when we initially started that, it was creating 1 TB quotas. Okay, so this is what I just mentioned. The group directory. Each PI receives a 5 TB group directory, which they can use to share with their researchers. There's the maintenance command. For example, it'll show you when the maintenance starts. If the maintenance starts in 3 days, then if you started a job for 4 days, the job will not start, because the maintenance starts before your job would end if it started right now. So you can reduce the days. If this does happen, cancel your job that you schedule for 4 days and change it to 3 days and 20 hours, for example, or less than that. All right, so now CryoSPARC, let's see if our job started. Come back here. No. We don't need this tab anymore. And then I'm gonna go to sessions. It's still starting. Mine is still starting. Okay, you can increase the quality to 9 if you want. I just noticed some of the menus look a little blurry, and if you increase it to 9, it looks a little better. Okay, let me get a thumbs up of everyone who has a CryoSPARC session that already started. I see 1, 2. You can find the output log in this link, session ID, and then you can go to output log. And I'm not sure why, but I'm getting a display error in display. So I'm going to restart my session, but it should have started by now. It usually doesn't take 7 minutes. So I'm going to delete my session. I'm going to restart, and when I click this, it should have everything cached what I used last time, except I do need to select this. I'm going to start it again. So if yours didn't start after 5 minutes, then go ahead and delete it and start it again. Okay, when it does launch, you'll see the license here. You'll just need to accept that once, and then it won't pop up again. So CryoSPARC Live is active with each session, and so basically what you have is you're setting up basically like a workflow, and you have it ready, and then whenever you launch your live session, CryoSPARC is looking at a directory that you specify, and when image files are saved in that directory, CryoSPARC will start processing that file with whatever you selected in that configuration. That directory, there's not a way to directly connect data streaming to that directory. What you'll need to use is Globus Connect. Install this. on your desktop or your whatever machine you're using that has the data. And then we have a web page here that will show you how to connect to the ACES cluster. And then from there, you can drag and drop image files as they're created into the directory that you specify. And of course, you want to launch CryoSPARC with enough time. But in this case, if you can pause the live session, and then you can end the session, or you can start it back up and can continue your session again. If you're about to run out of time, you can cancel your job and launch a new job and start the session again, and it will start looking in that directory. So CryoSPARC Live, there's a Thunderbolt here on the left. You click that, and it'll bring you to CryoSPARC Live. Let me see if mine started yet. Okay, mine started. Okay, you should see this launch CryoSPARC when it's working, and it takes just a little bit to check my log again. Okay. Everything looks good. There's some. Just give that a little more time to load. Okay, so then you'll need to create a project first, and you need to specify a project directory. Then once you've got that created, and then you come to CryoSPARC Live, select the project, and then click New Session. And then you'll reach a page like this where you need to add configuration parameters and exposure group. You'll probably want to select this box here, show advanced parameters, and then some more of these parameters will pop up, and then you can fill all these in. Once you get all these filled in, the directory to watch, this is where you'll be saving your images that you want to process with this CryoSPARC Live session. And then once this is done, you'll click Apply to All here. And once you've got everything filled out, this light green button will turn to dark green. And then you can start your session. Okay. But we're not going to do a CryoSPARC Live, but you can work with that if you need to. And if you have any questions, just send us an email and let us know. But we had a few people asking about that, so I included these slides in this short course. All right, here's our contact information. If you have any questions, we also have a survey link. The second half is going to be presented by Gaya Yadav. He is the Cryo-EM Technical Director here at Texas A&M University. And we're going to take just a few minutes and get everyone caught up.
Hi, everyone. My name is Gaya Yadav. I'm, as Mike mentioned, I'm the technical Cryo-EM Technical Director at the Laboratory for Biomolecular Structure and Dynamics. And today I'm going to walk you through how to process the single Cryo-EM data for a single particle reconstruction using CryoSPARC. So first, I want to give you a little bit about what we have here at Laboratory of LBST. And if you have any interest in using our resources to collect the cryo-EM data, we can help you to do that. So we have we have all the 4 different capabilities of the cryo-EM. We can do single particle analysis. We can also do the tomography. We are in the process of we already got the instrument, but we are in the process of installation of the one of the latest uh, focused ion beam milling system, and it's supposed to be ready in the mid of the next year. We also can help you to collect the data for the microelectron diffraction, micro ED, and that's good for the proteins that's hard to crystallize. You can get some very tiny crystals. That's not good enough to collect X-ray data, but still we can use those crystals to collect the microelectron diffraction pattern and get the structure from those the electron diffractions. So you can see we have all four modules of the cryo-electron microscopy, and if you're interested, you can reach out to us. Here is the test data for the from our microscope, and we're going to process the same data. This one, but we're going to process the small set of the data for the time being. But this one is the 1-day data set, so you can see the individual side chains and even the spaces between the aromatic rings. So that's only is the structure. And the resolution is around 1.5 angstrom of the resolution the structure we reconstructed after the installation of the system. So here is an overview of how the cryo-EM workflow. So first, obviously, we need the sample. So you have to do a lot of biochemistry to get the as pure as possible sample. Then we prepare the grid, and then we collect the data. Once we collect data, we get this kind of data. You can see the individual protein particles. And then we do data processing. That's what we're going to do today. And then we get this kind of map. And we do model building using, if you have prior X-ray structure, or you can use the AlphaFold model to fit into the map and do the refinement into the different refinement software like Phoenix, ISOD, COOT, and all, etc., etc., etc. Here is the list, the list of some of the most prominent used the softwares for the cryo-EM data processing. So the Reliant was a few years earlier. Reliant is the most popularly used the software. Once the CryoSPARC released, then it took over the Reliant. But still, people like to use some steps to process in the Reliant. The system CryoSPARC EMAN2 is also can be used. It's a little bit hectic to use, but people use it for largely for the cryo ET data processing. iMode is also used for largely for the cryo ET data processing, and CPN is the kind of wrapper for the different softwares. So you can do like streamline the processing and then set up all the jobs, and then you can leave, and then it will finish all the processing together and finish from starting to end if there is no error pop up. So next, we're going to do the live processing, and we will go slowly. So whoever want to follow and follow and at least get the initial map for the test data set. Okay, so here is the workflow for the data process, single particle data analysis in the CryoSPARC. Obviously, you need the data collection, you need the data. And then first step is do the motion correction, because I will go through while we're doing these steps, why we need that. Next step is CTF estimation. CTF is contrast transfer function. And then we clean the micrograph and remove the micrograph that's a bad. And then we do particle picking, and then align the 2D classification and particle curation. We need to do ab initio reconstruction in 3D. Either we can do the ab initio, or we can also use, if you have a prior model, you can use that model to generate the map to use as the ab initio. And we do the multiple rounds of refinement, and then we get final reconstruction, final structure. So, and once we did the local refinement and post-processing, and we found out the resolution is not good enough, then we go back to collect more data and do repeat whole processing and increase the number of particles. That's usually help if you have a good particles. But if you have a lot of heterogeneity, you can still sort it out. But in most of the cases, it work, but still there is some cases not necessary it will work. Okay, so so here is the how the CryoSPARC project hierarchy it maintains. So it have one project. Then you can create different workspaces. Let's say you collect one data set, you create process one data set, you have one workspace, you have another data set of the same sample, but with, let's say, with inhibitor or some cofactor. You create another workspace on the same project, and that will keep your job separated from each other. So it will be easy to manage the data and then data accurate later on when you need after like years. So next is here is the when you start the CryoSPARC session, you will see that's the home page. It will show up. It will show up the processing history. That will show all the projects you have been running at different last year. And then we also show the job by month wise, how many jobs you run every month. And then it also show the uses. And then at the end, it will show the how many jobs are running or what and how many are waiting. So you can see that if you all the jobs, you don't have to go too deep into the workspace to see whether the job is finished or not. You just go to home page and you can find whether job is finished or not. Okay, that's the overview of the home page. And next we're going to run we will go through these slides while we're processing the data. So let's start the process. So I hope that everyone has the home page up and running. Okay, so the first step in the single particle data analysis is let me see. So there is the question how to open this home page. So what you need to do it if you have this CryoSPARC running, you see the launch. When you hit the launch, it will ask you the username and password. So use this username and password, and then that will once you put these credentials, it will bring you to this home page. And then you click like on the left top corner, it's have a home page. You can click. If you're not, you can click that. Then it will bring you over there. There is another window like all projects. You can list the projects. So these are my project I have already run. And then and next I'm going to create the project here. So if you go here, you can see either you can, if you want to go particular project, you can select here. It will directly go over there. Or you can click select any of the project from this list. It will also bring you over there. So how to create the new project? If you look on the right top corner, say that new project. You click that new project, it will show up, pop up another window. It called the shows the new project. On the new project, you have to put the title. So I'm saying that CryoSPARC demo, or let's say short course. So that's my title. You also need to provide where is your files or where you want to save your files. So you can click this the folder. It will open up this another pop-up window. You can provide the path here. So our files are in this. You need to save your files in your Scratch directory, as Mike mentioned, because that's the only space you have, large space. So I'm going to here Scratch user. And if you click that one, you can, if you hit enter, you can see the list of users. My user, you need to put your username. If you put that, you can see my username here. And then I go to my folder. Or you can create your own folder, it doesn't matter much. And then I can save files here. So that's all the processed data will be saved in this directories. And it will create another folder that's named as CS, and whatever name you put for the project directory, CS CryoSPARC short course. So I select that, and you can see here there is another. If you want to put some description, let's say what the data is. So let's say put the CryoSPARC short course November 2025. Okay, so there is an option you can click create an initial workspace. You can create here, or you can also, if you don't want right now, you can also create it later. So I would say the all course, and then you can say hit the create. Once you hit the create, you will see the another home page is come out on the shows up, and let's have a list of different jobs. So you can choose the list and the whatever the job you want to run from here, or there is on the right side you see the hammer. You can click on the hammer. It will show up the list of the jobs. You can also put the, like, let's say I want to import. First step is to import the movies. So I want to import. Just put the IMP. It will list up all the jobs that start with IMP. So you can choose, okay, I want to import movies. So either you can do from here, or you just simply click this, I want to import movies. So to import movies, sorry, excuse me. So let's go through this slide to help you to what the import means. So import movie, what it will do, it will bring the movie frames into the program. Then next, we will do the patch motion correction and CTF. So to import the movies, we need some parameter. So here are the parameters we need to fill in that while we importing the movies. So these parameters for this particular data set, but if you collect the data somewhere else, the facility will provide the data collection parameters, and you will need to use those. Parameters for that while importing the movies. So here, movie path. First, we need to define where are the movies. So let's check where are the movie. Okay, so Scratch. So our the movies are stored in the Scratch, Training, CryoSPARC, CryoSPARC's Cryo Center. If you put this path in your directory and hit enter, it will show up the apoferritin. You can click the apoferritin demo, and then you have the movie folder. Once you click the movie folder, you can see that here there are TIFF files. So you don't need to select any. Uh, that's the you can click this. And what you need to do here, since we want to select all the files, import all the files, what do? We do put the wildcard, and then it will import all the files. You can see here. Then you say select. So you can see on the left side in an import movie, the window, it already showing the where is the movie located. Next, each instrument has the camera, and camera has its own the gain, because different camera had different effects. So you need whenever you collect the data, wherever you are, wherever you collect the data, you need to ask them this facility to provide the gain file. For the demo, we have here the gain file. So we go click on the folder. It will bring you down back to the same folder. Go one up directory, and then you will see there is the gain file. You can select that and select enter. And if it was provided, some camera might have a defect. So the facility should also provide you the defect file. If defect file is provided, you need to import it here. Since our camera does not have any defects, so we don't need any any defect file. Then, since you also need to know whether there is any rotation in the gain file or not. Okay, usually they have rotation or flipping. So you need to know whether there is any rotation or flipping. And if there is rotation, which direction? So our camera has the float rotation on across the y along the y-axis. So we need to flip the gain along the y. We don't need to rotate; it just flip. And next, we need to provide the pixel size. So here is the pixel size. Our pixel size in the movies are 0.326. You can put here value 0.326. And you also need to know what's the accelerating voltage for the microscope. Some are 200 kV, some are 300. So ours are 300 kV. And you also need to know the spherical aberration for the microscope. For the new microscope from the thermofisher, usually this value is 2.7, but it's better to confirm with the facility what the value you should use. And then when we collect the data, we also use the particular amount of the dose applied to each image. So for this data, we have a 42 electron per angstrom square. You need to also provide that information, 42. And if you negative standing the data, you need to click that. But if you have a cryo data, we don't need it. If you have faceplate data, you need to check this one. And so rest we keep it the default. And then you say queue the job. Once you queue the job, you see that it is started and then running. We only have 25 movies. It's fine. Just we will get some low resolution map, but that will not have any effect on the later on the data processing. So if you click here on this square, it will show up the images. So these are individual protein particles. You see that this is apoferritin. So apoferritin have 24 subunits, and they form a kind of a ball-like structure. So you can see like a ring-like structure here. Okay, so once it's done, you see that it turned into green. Previously it was blue, now it turns green. So next step is to run the motion correction. So we're going to run set up the job for motion correction. So there is two way to run the next job. As I mentioned earlier, either you go to job builder and then you click right down here, motion correction, patch motion correction. You will see that it's a list of the jobs appear. Or there is this newer version of CryoSPARC. They have another feature. If you click three dots here, it will also show up the list of the next step. So you can see that what do you want to do? You want to clear, restart, or whatever, delete job. If something wrong, you can delete it. And then we also have what next job you can run from this and using the inputs from this job. So we want to build patch motion. So click the patch motion. So good difference between building the job from this job builder and running directly from this previous job is it will if you run the start if you start building the next job from the previous job, it will automatically take, import all the required inputs. So if you look here on the right side and where it lists all the parameter for this job, patch motion correction, you can see is movies already imported into the this job. But if you start the job from here, you have to manually drag those files, like drag those files from here like this. But if you start from the job from here, the input files are already imported here. Okay, and then it's have a make motion diagnostics. You can have different parameters. You can go through mock diagnostic plots. So, and then if you can also post, let's say you have several thousand images, you want do the quick processing. You can select how many movies you want to you process. So you see that it say the only process this many of the movies. So let's say 5,000 images. You want to say, okay, quickly process 100 images and see whether data quality is good or not. If the data quality is good, we want to process rest. If not, then maybe you don't want to waste time. So you can process 100, 200, or 1,000 images. So you can provide here the number, how many you want to process. It will only process that many images and then it will stop. Okay, but here we only have 25 images, so we're not going to do anything. We process everything. If your system is low memory mode, you can select this. Otherwise, sometimes if your system does not have enough memory and it need more memory, it will stop the job. So if you click this one, you select this one, it might still run. So save results in 16 floating points. This is sometime save the space and make the processing faster, but some of the processes are not compatible with these kind of images. So it's not a good idea to select this for this option. Output inverter training, yes. Number of movies, that's fine. You can leave those the default values. And these files are the data was collected in super resolution mode. And you can see the pixel size is 0.326. So usually the resolution is limited to like the Nyquist limit. And Nyquist limit is usually the double of the pixel size. So that means the Nyquist limit for this data set is 0.65, 0.65 angstrom. And that's really hard to reach at that's resolution. So it's better to make the image size smaller. That will help to process the data faster, and also all the processing will be more smoother. So what you can do at this step, you can say, okay, I want to do Fourier cropping. We're not doing in real space cropping, even though we do based on the Fourier cropping. So even if you crop like your files are half in the size, but your information in the images will still preserve. So it will not affect your final resolution. So here is another option. You need to use it. So you can, if you remember, like when we import the movies, we have the total dose applied is 42 electrons per angstrom square. Here, if you have some defects on detector, you can, and it has like a very high values for particular pixels. You can say, okay, any value more than 42 should be replaced with 42. So your images, from your images, we call hot pixels. That hot pixels will be removed during this process. So that will help you to get better noise model. So this is important as well. And if you want, you can use the variable dose. If you have some kind of you collect the data at a different doses and then you want to process it, then this will, you need to select this option. And then you need to, next thing is how many GPUs you have. So since we have only one GPU, we can have left it, leave it default. But if you, let's say you have 4 GPU, you can put here 4. And then you say queue the job. When you queue the job, you can say it's launch. Now it's started. Once it's started, once it's running, it turns from the gray to blue. And now if you click that, open up, you can see the progress of the job, what's right now is doing. So you can see here, it's processed the first image and in 18 seconds. And it also depends on the GPU type. If you have the higher end GPU, like we have here, H100, it takes it take 18 seconds. If you have a GPU that's have only have like a 24 GB memory, it might take 30 seconds. So, but it not take like a double of the time. Slightly, it might be 30 to 40% higher, but not the double or triple. So here you can see the different plots. Is here. So what it's doing is, when we collect the data, it has multiple. We expose it for. We applied. Let's say another one. We applied 42 electrons. We cannot apply all 42 electrons to one image. So what we do it, we save the fractions, like 1 electron per frame. So we expose for a fraction of second and save one image, then expose another fraction of second, save another image. So By that way, we have here, we have a 42 images in each movie file. So that's why it's showing, it's measuring the drift and along X and Y between the different frames of the same image. So you can see here, it has the X, Y and X drift. And then based on that measurement and the feature on the individual frames, it tried to correct that drift and align those individual frames and generate one single image. And that single image, after the drift correction, it's showing the here is the thumbnail for that particular image. So if you look, if you compare this image with the one imported image, you can see there is a huge difference in the contrast. This image and this image. You see that they are more, there is a higher contrast and they're less blurry, but it's a down sample, so you might see some feel like it looks like a blurry, but it a down sample 8 to 10 8 or 12 folds, so it's really a small image. And here is showing that each particular so why say patch motion? What you do it generate different patches on whole image and track those patches through those fractions. That's why it's called patch motion correction. So it's only track individual patch on different fractions and then try to align it together. That's why it's called patch motion correction. You see this image looks way better than the one imported. This image is at low defocus, so the quality is still good. Just its defocus is low, so the contrast is also low. This is completely higher defocus, so they have a better visibility and better particles. So once and this is fast, you can see that our 25 images are finished. And now job is turned to the green. And then we want to find out more parameters about the images, like what's the defocus used to collect the data? What is the contrast transfer function? So this function to find out those parameters for individual images, we run build the patch CTF. So the patch is again the same. It will make the patches from multiple patches on each image, and then calculate those the parameters from different patches, and then combine those patches to create those parameters for like average for each image. So you go click the three dots, and then if you look quick actions, there is a patch CTF estimation. When you click that one, it will open up another job submission tab. And then you can see it's already imported the micrographs from the job 2. Job 2 means that's from the motion corrected micrographs. And then again, you have the same kind of parameters, how many images you want to plot, how many you want to process. And then usually we don't change these parameters, but uh, you can select the, like, let's say you collected the data at your low defocus. So the maximum defocus during the data collection you use is, let's say, 2 micron or 1.8 micron. So you may not want to collect your estimate till the 4 micron, because I don't think any image you will have that's have a 4 micron defocus. So you may want to change this value. And if you starting defocus is 1 micron, so this is 0.1 micron. That might also be not possible. It's possible if you missed your during the data collection, your auto focusing was wrong. but usually we leave it default, and it's really fast, so not really matter. And here you again we have one GPU, so we can set the GPU, one GPU, and let's run, queue the job, and this should be, I guess this CPU job is slower as compared to the CPU. So I would usually like to run the CPU job in place of the GPU for CTF patching. So you can see it's fast. Let's see. Oh, it's not that bad. It's fast. So here, what it's doing is it's measuring the contrast transfer function, and it's plotting at a different defocus. You can see here, and the peak is found. Whatever the peak is found, that's the correct defocus of that micrograph. And then it try to since it's kind of like a wave function, so it's have a theoretical plot, and it's a different ratio, sorry, the frequency, and it's calculated from the image. A plot in this here both, and based on this plot, you find out what's the estimated resolution from this image possible estimated resolution. So the possible estimated resolution will be like where the two curves, one estimated and one calculated from the micrograph, cross each other. That's kind of the resolution limit the micrograph have. So this plot is important. This is same data that's plotted in 3 dimensional, and you can see that another similar plot, but it's plotted in wave function. So you can see that the calculated and theoretical are matching very well on here. Once they start to cross each other, that's a limit of resolution from this image. So you can see the estimated resolution is 2.17 angstrom, and that's a really good data. It also plot based on the distribution of defocus. It can also estimate the ice thickness, but this is not very conclusive. So we largely look for the estimated resolution, and that's how we look for the data quality. And you can look, most of the images are fit around 2 to 3 angstrom. You see 2.8, 2.4, 2.2. So that's the data is really good. Okay, so this one is finished. So next step is data curation. If you have some, like when you collect the data, obviously all images will not be good. So what do we do? We do the exposure curation. In exposure curation, we discard all the images that has the bad CTF fitting. So this is the interactive job. So you need to, when you run this, it will open up the plot that has show the defocus, list of the images, and average defocus. It will also show up the CTF fit resolution. You can see. So lowest is 2.17 and highest is 2.9. So as long as it's fit below 4 angstrom, anything below 4 angstrom or less, we still select those. We don't need to discard. But anything we have like 6, 7, 5, I usually discard those images. You can simply drag this bar, and then you say, okay, I want to set this threshold. I will remove the images the images which not fall in this threshold. And it also show you how many images are selected and how many rejected using this threshold. So here is fine. I don't have to discard anything. That's the resolution. And intensity. So you can also select the intensity, like the average intensity. So if the image have very thick eyes, the intensity will be lower. So anything like you can discard those images. You can select, okay, I want to discard this images, something like that. By that way, you can discard those. And relative ice thickness, you can also select those. Like, okay, you want really thin ice, you can do this, but no need here. And if you want to discard like the images that have like drifted in between the frames, so you can select this same as other parameter. You can also do this here and discard the images that have a bad drift. Usually, if they have bad drift, they are not good. But anything like a 50, 60 angstrom, they're fine. Pixel, it's fine. And it's here, you see that it's a 62 pixel. Our pixel size is 0.32, 0.5. That means around 25 angstrom. That's okay. And then once you're happy with those, you can say done. And it will save up the images. Here, we did not discard anything. So it's showing that all are accepted. But if you say you have removed, discarded some, it will show the plot, okay, 10%, 20% are discarded. And the next step is to do the particle picking. So for the particle picking, first what we do it, you can, if you want to be more precise, you can do manual picking. We go click the manual picking. It will automatically uh, import the the input for this, and then since it's manual picking, it will ask you to pick the particles. What is it? Okay, so you can see here the list of exposure plot, list of the images, and then you have here the particles real image. You can scroll down to magnify or zoom in, zoom out. Here you can select the image. It will show up here. You can see. So we can do this. What do you need to do? Select the image and then try to pick some particle. Just what you need to do. Here you select the particle diameter. What's the box size you want? I will talk later how to uh, what the box size and the particle diameter you need to use. Usually the particle diameter we use is longest dimension of the particle. So the apophotony is around 140 angstrom. So maybe we can use 140 here. And then if you left click on the center of this particle, you will see that the inner green circle is showing the particle diameter and outer square showing the box size. So usually the box size we prefer to have around 1.5 to 2 times of the particle diameter. So here is, so let's calculate how much box size you need. So our pixel size is 0.65, let's see, 0.326 times 2 because we did the Fourier cropping. So it's a 0.652. And our diameter, how to find out the pixels from the diameter. And so 140 divided by 0.652. That many pixels we need for the particle diameter. We want to 1.5 to 2 times. So 360 is good enough. Okay. You click like this. You can click, even though they are a little bit overlap, is fine, as long as they're not overlapping on each other. It's always good. The manually picked particle are the best particle. And if you, let's say you click somewhere in the middle and that's not particle centered, you right click on it, it will remove that location, the selected area. You also don't want to pick anything very close to the edge. That might have some empty area. So this is the how you pick the manually. So usually like a few, for this sample, if you have large like the apophytin or virus sample, maybe 1,000 or 500 to 1,000 image particles may work. But for some other like small proteins, you might need more, at least a few thousand particles. That's a little bit pain, and that's a little bit pain. For this kind of sample, we can pick the particle from like a 500 or something. It might be enough for to generate the initial 2D classes that can be used for the ab initio for the template-based picking. Usually, the template-based picking work better than the blob picking. I will also show you guys how to do the blob picking. Uh, you can see here it's showing how many picked. Hey, Mike, do you know how many people have been following this?
We have 4 people that logged into the portal, and one person just gave a thumbs up that they're following along.
Oh, that's good. I will only select from one image, not many. Let's see whether that work. It should work. Okay, I picked from one. Okay, once you finish one image, you can click another one and do the same thing. If you lost it, you can do this. And then once you have enough, I have 246 particles. It might be okay. And then you say, okay, done picking, and then extract particles. Usually the manual picking, you can see how good it is. They also extract the particles in manual picking, but if you do the block picking, it will not extract them. So we can do, once it's picked, you can run the, like if you click these three dots, you see the build 2D classification, and okay, we can select the 20 classes, or we can do, because we don't have many particles, so we can do like 10 classes. And then what the minimum resolution is okay at this point, we do not really need it. And then initial classification uncertainty default is 2. You can leave that, or you can change around 1. Since we know the diameter of apophethrin, we can put it here. Okay, I want to 140, so let's say 160, slightly give the some room, extra room. And then we want to recenter. If let's say we try to, if you look in the extracted particle, they are largely centered, but if it is not centered, it will try to center it. I'll usually put the 5.5 here to force it more. And then you can also put the pixel size for the micrographs. So 0.652. And then we have one GPU, that's fine. And another thing I like usually do it. So this is usually 20 iterations online EM iterations. That's a usually default is 20. So you usually I increase this to 25 to 30. So that will increase the better classification. And one thing I also like to do it, I do hard classification. So this classification is relative. One particle can be assigned to multiple the 2D class averages. So I want to make it okay. Do hard classification. So have one particle can be classified into one class average. And then you say, you know, so you can see just 200 something, 260 particles, 240. Since they are manually picked, so well centered, so you can see that too, a couple of good 2D class averages. It will also show the resolution plot, how was the information has. So while it's running the 2D classification, we can also do the uh, manual how to do the block picking. So if you go to three dots on the curate exposure, so you see that build a blob picker. You can click that. It will ask you what is the diameter of the minimum diameter. So I will say 100, and the maximum I know is 140. So I would say 140. It will add some extra, but I will do this. If you have like elliptical, you can this, but I have a circular particle, so I say then okay, and then say okay, uh, run. So you can see this one, the 2D classification has finished. So we want to, next step for this one is select 2D, good 2D class averages. So we go to select the 2D class averages. How you do that, click the three dots, Q select 2D classes, and then it will open up this. And then you can simply select these, okay? These are three. I want to, not even this, just three is enough. Let's do five, four. We select these four comparatively better one, and then it's a done. We have a good reference template for the template picking. And this is auto. You can see it's picking, but its centering is not very good. So either you can try the different parameters for the low and high diameter. That might help. We can try again. We can say restart, clear the job. If you want to restart the same one and clear, and then you can say, okay, the maximum I want 120. And let's see how this goes. It's a fast, so it's okay. So you can see it's going to, no, it's make it worse. So clear, build, let's say hun, clear, stop building. So let's say 150, 110. So you have to do some back and forth processing to find out, to center the particles. Once you find out that, and then you can run. You can do this if you have several thousand images. You can do this for 100 images or 50 images. Once you find out the good parameter, you can run it for every whole data set. But you can see still it's some are centered, some are not. So I will still go with these one. One we did the manually pick the particle and 2D classification. And then what I do it, I will do the go to curate exposure, and then I will do the build the template picker. Template means I need to provide the template what to pick. Since we have 2D classes here from the manually picked particles, good one. So I will use this as a template. So you can see you run the template picker and then click this, open up this job, and then it has the different outputs. You can drag this template to the template jobs. You see that it goes there. And then you have a micrographs, right? And from the curate, you can, the micrographs are already imported because we run this template from here. And then particle diameter, we know this is a 140. And yeah, so you only need to provide the template and then particle diameter. And then if you have so many, you want to try how good is picking. You can do the how many 20 or 50 micrographs, and then once you find out good parameters, then you can run whole data set. But here we only have 25, should be okay. We might have to run one or two more times to find out the centering. So you see that it uses the 2D classes, and you can see they are already pretty centered. The picked particles are very centered, so you don't have any problem here. So you go check all those, you see that template picking works very, very well as compared to the blob picker.
Hey, Gaia, while that's running, let's take like a 10-minute break,
Okay, yeah,
and we'll come back here. We'll start back up at 3:15.
yes.
All right,
Okay,
thanks.
see you. Okay, so welcome back. Uh, we done the template picking, right? So you can see here the picking is really good and it's finished. So the next step, what we do it, we do the inspection as we in when we run the CTF, we do the curation. But when we do the after template picking, we want to check the particles, say inspection. So inspect the particles, and you can see here the plot, number of picked particle from each different micrographs. And then another thing you see here, the plot is our histogram and then NCC scores. So the usually what you need to do here, you need to slide this bar and check how the particle pickings is affected. See that if you make it the lower limit is too high, see most of the particles are unselected. So slowly go down and go down until you see that most of the particles are picked, but the background is not picked. Right? If there is some background picked, it's fine, but not too much. And then you can see like there is some ice contamination that's also picked. So what I do, we remove this, reduce the higher power power, and then that will remove the particle picked from the ice or anything that's very high contrast. You see that it's going away. So you do it until you start to see like, okay, your genuine particles are still picked up. And then if you want to see them better, reduce the particle diameter and you can see them better now. You can also play with the NCC score to remove the particle from the noise. You can see. Now you see that most of them are picked and nicely picked. So that's I set up the parameter for one image. What I do usually, I go to different images and see whether this is correct for all of them. You can see this one have an ice, separated ice is just excluded very well. See that? So this is the beauty of the template picker. And I only picked the 260 particles, and that's everything else is way better, more accurate as compared to the block picker. Once you're happy with this, you say, okay, done with picking. And it will, so you can see here the particles. And then next step is, this usually is very fast. Next step is we want to extract. When you do manual picking, it automatically extracted. And as long as you selected that settings when you submitting the job. And sorry, yeah, once you have inspected those particles, there is another new features in the new version of the CryoSPARC. You can also queue the junk detector. So whatever we did by that way, we can also do the junk detector. So it'll remove the particles from the ice. And also, if you have carbon surface in the images, that's also remove the particle from the carbon surface. So rejection distance, you can select this and then simply just click hit Q. And then it should be faster. I will show you as this one later, but we have good particles, so we can directly go to the extract. Build the extract from the micrograph. we can do the, since you see already using one GPU in junk detector, so we can do the run the CPU job, just CPU. Oh, it's already done. So if you go click here, remove like 4% particles, that's from the junk. And then 96% particles are good one. So you see that whatever we removed manually, it did the same thing uh, while did the junk detector. But it cannot remove the one which is from the background. So we may still, after this, we may still want to do the inspect the particle curation. But since we already did it, so we directly go and build the extraction. Since, okay, if you run the extraction from this inspect pics, it will already incorporate both the required input, micrographs and the particles. We have one GPU. If you have more, you can put the more GPUs here. If you don't have GPU, you can put the remove, you just put the 0. It will only use the CPU. Then you need to provide the box size. And we calculated 360 is with a little bit, 360 looks good. And here the pixel size, if you have large data sets, you can crop it, make it a smaller image, make it that will help you to process the data faster, because the purpose of the 2D classification is to remove the junk particle. So better to run faster, and you can able to separate out the junk particle from the good particles as quickly as possible. So I'm not doing that here because we don't have so many particles. We only have, we can still do it. Let's say we have 360, right? So 360, if we want to bin by 2, divided by 2, so it's 180. 180. Let me see. 164 times 4 divided by 0.645. No. Even we use 328, it still is fine because that's almost slight kind of like almost 2 times of the particle diameter of the apophretin at 140, right? So then you can do it 164, and that's the crop, Fourier crop. That's I'm binning by 2. So if your box size, original box size is 328, it will the final box size will be 164. That's half of the 328. 328 divided by 2, that gives you 164. And that will like image size will be half, and then processing will be almost 2 to 3 times faster. And this is extraction. Automatically just use one GPU. It doesn't matter how many GPUs you have. So it's usually it's a little bit slower. And then once is extracted, we can run the 2D classification from this. We have large number of particles here. How many? We can do 50. Maybe 50 is still too many. So let's do 30. And resolution, you can provide this information, not really needed. Mask diameter, let's say 160, work well for the manually picked particles. I will also say the center, and then hard classification. Hard classification. So here there's some features like enforce non-negativity. So if you have very small particles, let's say 50 kD overall size, just 5 nanometer, this option helps, but you don't need for this kind of particles. And then we can put the number of GPUs here. You can put as many as you have, but we have only one, so we're using one here. Yeah, we have how many particles we have? We have 16,000 particles here, so it should be okay. Not too far, too slow. And then you can see here classifying into 30. You already see there's some good ones. And while it's, you can now already start to see the helical features in the 2D classification. You see that helices? That tells you like some of these classes are really, really good ones. And you can also see the monitor the number of particles. So largely most of the particles are in these four class averages. Everything else only have very few, like 7 particles, 8 particles. Here it has some 200 particles, but largely they are 500, 400, 300, 200. And this is only using the fraction of the particles. So that's why it only have a few hundred. In a lot, couple of last iterations, you will see these to the thousands. Because we have originally we have 16,000 particles. There is only few 4 class averages. So they might have some 500, 5,000, some might have a 4,000. So you see that now you have 2,800 particles. Once it's happy with the classification, it will, based on that classification, it will classify rest of the particle into these classes in last iteration. So that's already finished. And now you can go and select the 2D class averages. We select the good ones from here. So we only select these 4, not going to select anything else. And you can see here out of 16,000, only 9,000 are good and rest are completely bad ones. So next we can do the next step in this process is make the ab initio. So either you can use the ab initio from the previously known structure, or you can use the reconstruct from these images. So we will do from here. And ab initio, how many you want? You can ask you multiple. Let's say I ask 2, and then how many number of particles you want to use. Okay, I want to use everything. Since we only have 9,000, so it's better to use all of them. And you can see that you will see how the 3D volume was generated. So what it's doing it here, it used the individual particles, and then initially it select like, okay, we have a ball-like structure. And then it individual image, it tried to put on that ball and try to do what we call the 3D rotational averaging. So it rotate individual particle in 3 dimension and try to fit into one and overlap with previous particle if there is any overlapping, and that's how it do the 3D rotational averaging and reconstruct the 3D map from these 2D images. Initially, you can see almost there is nothing, or only the blob. So we ask two classes. So you will see that initially they are kind of same, not much difference. Just a blob. And you will see over slowly, one of them will be populated and other one will be bad. You see this? And let's see this one. See, way better than the first one. So slowly getting better. And you can see here the difference. So this is the one volume, that's another. Uh, and if you look on the right hand side, so the unused, it's only using the 64 particles right now. No, 90 particles. Out of 90, in one class, it have a 26 particles, while the other have the 64 particles. So the map I shown you, that's only from the 64 particles. Once it's in uses when later iterations, when it use the more particle, the volume will, the map will be improved. So now you can see it's way better as compared to the previous one. It's getting into shape. Let's see how this one looks. Looks like number 2 has more particles. You see 2800. Number 1 have 6000. So that's why that's the reason you can see that have a higher more features as compared to the second one. You can these are individual alpha helices. You can see here in the these are alpha helices. Let's see. Usually this process is slightly slower as compared to the other processes, because it's doing the 3D match 2D matching of 2D images to the 3D volume, and then classify into two class averages. But it's already looks good. You can see that the number of particles matter a lot. It's already getting into shape. So okay, why this map, the second one looks better, but the original map looks bad because of the orientation. This is showing the side from side view. This is showing the top view. You can see here. So this is first one is from the side, and the second one is from the now it's rotated. Okay. You can see that it's more and more features are coming out, and one now it's done. So Okay, so what I'm going to do it, we have some rough volume. I'm going to use this as an initial reference and then refine the map. So what I'm going to do, uh, go here, say non-uniform refine. You can do homogeneous refinement. Uh, what the regular process is, first do the heterogeneous refinement. We can do this from here. You see that if you see the list of the available jobs, we can run the non-homogeneous, non-uniform refinement and heterogeneous refinement. So run the heterogeneous refinement. Okay. And it will do the automatically take all the parameter, the inputs from this ab initio job. Usually this is fast. This usually people use this as the classification, so it's have a better classification as compared to the ab initio. But those two maps looks kind of the similar, just it's have slightly different. We can do the processing individually and also do the combine the two data sets and refine into one. We will check, we'll see how it goes. So we can do homogeneous refinement. And then in homogeneous refinement, we need the particle set and we also need the volume. So I'm going to use this volume, looks better. Okay, so that's the zero. So initial volume and then total number of particles. Okay, I'm going to refine it into C1, but I know that it have a octahedral symmetry, and I can apply that symmetry to help it improve the number of particles, apparent number of particles for per monomer, and which that will improve the resolution. Maybe you can stop this. I killed that job so to make it fun to run the homogeneous refinement and see how it goes. But usually, because we also running out the time, so I want to show you guys how to go reach to the end of the data processing. So these are the steps. After this, you run the heterogeneous refinement. After heterogeneous refinement, you do the homogeneous refinement. And after homogeneous refinement, we do another round of refinement called the non-uniform refinement and apply the symmetry. And you will see the effect of the symmetry on the resolution. Okay, it's reached to 7.5 angstrom. Not very good, not convincing. But we can see it. Okay, let's do run the homogeneous refinement, non-uniform refinement. So go to non-uniform refinement. You can include this, and then I will still want to use the volume from here. This looks better than this one, so I want to use that one. And we know that we have octahedral symmetry. Okay. Okay. Let's firstly run a little bit more. So this is the problem here is only we have 9,000 particles. So we still have overall structure, overall map, but we don't have because of the signal to noise ratio at this number of particles, it's not that good. So it's stuck around 8 angstrom, but it still is have, you can see all the parameters like the curves looks okay, not bad. But when you run the non-uniform refinement with octahedral symmetry, you will see it improve the quality of the map. There will be day-night difference between the two. You can already start to see. So why it matter is, so when you apply the octahedral symmetry, so it's kind of like particles are 8 times more than the original as compared to the C1 symmetry. So we have like 9,000. That means if we apply the octahedral symmetry, I have 9 times 8, like almost like 72,000 particles. Once we have kind of 72,000 particles, the signal to noise ratio can be improved way higher than as compared to the 9,000 particles. So you can see already we start to see the very high resolution in the features, and you can see here. So now you show up the like, okay, real apoferritin. You see that? Even at with this few number of only 25 micrographs, if you look carefully at this, if it's not done yet, but this is one of the heavier side chain, the aromatic rings. You can see even like slightly cut inside, and you see that side chain, the heavier side chains. You can see them very well. So you can see the homogeneous refinement and non-uniform refinement with octahedral symmetry, how the symmetry affect the reconstruction. Similarly, if you have C1 symmetry, that means if the some the sample that have a C1 symmetry, you need at least like multiple times of higher number of particles as compared to the one that have symmetry. So the particle that has symmetry is way more easier to do reconstruction as compared to the one that does not have any symmetry. And if you look the event log, you can see here, we already at 2.69 angstrom resolution. And our pixel size is 1 point because we crop it to half. That means our pixel size is 0.652 times 2. That's 1.3. That means our Nyquist limit here is 1.3 times 2, 2.6. So if we look here, we already at the Nyquist limit, see, 2.6 and 2.69. So what we need to do here, we go back, once it's finished this job, while it's, we can also do, while it's doing, where is the extraction? This. So this is completed. What we can do to improve to make the, uh, first thing, let's discuss these results. So you need to look here what the global spherical and the Fourier FSC, Fourier scattering correlation. That's kind of like the same kind of the plot. We divide the data into two and reconstruct those two data, two part of the data sets. And then what we do, we try to calculate the cross correlation between the two maps. And that's what is called the FSC, Fourier cell correlation between two maps. And that's how well the two maps are overlap with each other or have better correlation. That's how we define the resolution. So FSC cut at 1.143 is used as the resolution cutoff. So here it says without even any mask, you have 2.8, with the corrected 2.7. So it's 2.7, 2.69. And what we can do next is it's also the spherical, the CTF that also looks clean. So what we need to do here, look here, if you have something like a very jump in CTF fitting. If you have some jump, that means something going on, or the signal at particular resolution is not good, or the construction is not good. So the next step we can do it, we can extract those particles. So we can do this. Go here and we can clone this job. And in place of putting this particle 16,000, what I'm going to do it, I'm going to use the particle from here. So all 9,000 particles, the micrographs are already there with GPU. I'm not going to crop this time. So I will have the better, the, the images that have a higher resolution information. And from this, I'm going to run again the non-uniform refinement. So what I do is to make it faster, I clone the parameter from this job and I use what I do, I will use the volume, initial volume from here, previously refined one, and then I will use the particle from here. That's I re-extract, okay? And then we have already symmetry octahedral, okay? And then don't need to change anything just for the testing. And we will see the better FSC and then this map, because we will see better featured map in the new refinement. Since the image size is larger, so it might take a little longer slightly longer time as compared to this refinement. But we can what we need to do next is while it's running the non-uniform refinement, the next step in this process is you can sharpen, though it's a sharpen automatically, but you can run sharpen, and you can apply the different B factors. If you go here, and then you see that if it's also plot it's also do the linear plotting, and it found the B factor 62. That's kind of negative 62. And you can apply here, okay, I want to apply different B factors, let's say 50, who are there is 60. So you want to filter it a little more, you can do 50. You try different the B factors and see which one is better, and still you not have fragmented density, but you can have a better side chains. And you can use this threshold, play with different threshold and see which one work best for your particular refined map. And based on that, you can it might have it might help uh, boost the resolution. Oh, guess I did not provide the clear inputs. Okay, so we have the volume here, but we also need to provide the mask. So here you can generate your own mask, very tight one. So you don't have to use the one which is system generated. So you know your mask better, which might help to improve the resolution or make the FSC better. You can see here the FSC is way more like smoother. And you can open the map and check how it looks. If it looks bad, you go back and increase the B factor. If map looks better, and you can try even in decreasing more the B factor. So that's how we use do the sharpening. And after sharpening, we also have the option like we do the local resolution estimation. And there is another like a CTF refinement, because the CTF is calculated from the whole micrograph. You can calculate the CTF for individual particle images. So you can run the CTF refinement and then come back and do the non-uniform refinement. Usually that helps to improve resolution slightly. If you have a lot of variability, like you have conformational changes that change, you can run the 3D variability analysis. It would try to find out which part of the particle is variable or moving. Based on that, you can define, okay, how the let's say you have particle, you have a cofactor. When it bound to the protein, there is a local conformational changes. So this can identify those kind of changes, and based on that, you can find out the mechanism how the the variability is there, how the when the cofactor or drug or inhibitor bound to the particular site, how other parts are affected by the binding of the molecule. So this is useful for doing that kind of the analysis. Oh, yeah, so overall the resolution still looks the same, but I guess something is happened here. So somehow the pixel size is still using the same. That's why not improved. And let's see.
Gaia, we've reached the 4 o'clock mark. If you want to continue working, just so we can have the recording complete, can you have time to finish up, then you can keep working.
Oh, we we done.
Okay.
So yeah, because whole the procedure is same. Just we need to go back and forth, do more and more processing. Overall, the procedure is we done. Like from importing to the non-uniform refinement, and then another one step is we do it CTF and then local resolution estimation, and we can do based on that local resolution estimation, we can move this information to Chimera and color our map based on the resolution in different parts. So that's the only thing. And other than that, we can run the Chimera on our. We have this Chimera X. We can launch those. This it's fast usually. It's taking time. So oh, it's already running. So you launch the Chimera. You can open those files. Okay, so what do we need to do? Look, job number 18, right? Go to 18, and then you have map here. So this, the sharpened one, you can open into Chimera. You will see here, you can see it better, right? And you can analyze your map here and do the model building and initial model building here. You can fit the model here, and then you can use the Phoenix to do refinement. That's the kind of like a complete procedure how to process your single particle cryo-EM data in CryoSPARC, from importing to the non-uniform refinement, local resolution estimation, and then non-uniform refinement, CTF refinement, and then finally the local resolution estimation. And at the end, you do the model building in Chimera, and finally the refinement, model refinement into the Phoenix or Coot or ISOD, this kind of, or even Rosetta, you can do in Rosetta. That's kind of complete overview and the workflow for the data processing in the CryoSPARC for the single particle. Okay, so if you have any questions, yes, I'm available. You can email, you can reach out to my phone number, whatever method you like to. And thank you for attending. Yeah, I'm done.